Hello friends, welcome to this YouTube channel. Today we are going to solve a couple of numerical problems on resistance. By solving these problems, we shall learn how to compute resistance of a conductor, comparing it with another conductor of known resistance. When temperature remains unchanged, the resistance of a conductor is directly proportional to its length, that is, R is proportional to L. It is inversely proportional to its area of cross section, that is, R is inversely proportional to A. It depends on the nature of material. Now we can write R is proportional to L by A. Therefore, R equals to rho into L by A, where proportionality constant rho is the resistivity of the material or specific resistance. When L equals to 1 meter and A equals to 1 square meter, R equals to rho. Hence, specific resistance or resistivity of a material is the resistance offered by 1 meter length of wire having an area of cross section of 1 square meter. There are two wires A and B of the same material. A is 20 times longer than B and has 1/5 of the cross section as that of B. If the resistance of wire A is 5 ohm, we have to calculate the resistance of wire B. Let the resistivity of the material be rho. For wire A, given resistance Ra equals to 5 ohm. Let the length of wire be LA and cross-sectional area be AA. Expression for resistance of wire A, Ra equals to rho into LA divided by AA. For wire B, let the length of wire B, LB and cross-sectional area be AB. Expression for resistance of wire B, Rb equals to rho into Lb divided by AB. According to the problem statement, where A is 20 times longer than where B, therefore LA equals to 20 times LB, and where A has 1/5 of the cross section as that of where B, therefore AA equals to 1/5 of AB. Therefore, resistance of wire A, Ra equals to rho into 20 times Lb divided by 1/5 AB. That gives us 100 times Rb. Therefore, resistance of wire B, Rb equals to Ra divided by 100, that is equal to 5 divided by 100, that gives us 0.05 ohm or 50 milliohm. We have to compute the resistance of 1500 meters of a copper wire of 25 square millimeter cross-sectional area. The resistivity of copper is 17.24 microohm millimeter. We also have to calculate the resistance of another wire of the same material 3 times as long as the previous one and 1/2 the cross-sectional area. Let us first write down the given data. Resistivity of copper rho equals to 17.24 microohm millimeter, that is equal to 17.24 into 10 to the power minus 9 ohm meter. For first wire, given length of the wire L1 equals to 1500 meters. Cross-sectional area A1 equals to 25 square millimeters, that is equal to 25 into 10 to the power minus 6 square meter. Expression for resistance of the first wire R1 equals to rho into L1 divided by A1. Using values we get 17.24 into 10 to the power minus 9 into 1500 divided by 25 into 10 to the power minus 6. That gives us 1.0344 ohm. For second wire, given length of the wire L2 equals to 3 times L1, that is equal to 3 into 1500, that gives us 4500 meters. Cross-sectional area A2 equals to half of A1, that is equal to half of 25 into 10 to the power minus 6, that gives us 12.5 into 10 to the power minus 6 square meter. Let us now determine resistance of the second wire. R2 equals to rho into L2 divided by A2. Using values we get 17.24 into 10 to the power minus 9 into 4500 divided by 12.5 into 10 to the power minus 6. That gives us 6.2064 ohm. Now we shall determine resistance of the second wire using alternative method. R2 equals to rho into L2 divided by A2. That is equal to rho into 3 times L1 divided by half of A1. That is equal to 6 times R1. We have computed R1 equals to 1.0344 ohm. Therefore, R2 equals to 6 into 1.0344, that is equal to 6.2064 ohm. A wire of length 1 meter has a resistance of 5 ohm. We have to calculate the resistance of second wire whose resistivity is double of the first. If the length of this wire is 4 meters and the diameter is double of the first. Let us first write down the given data. For first wire, resistance R1 equals to 5 ohm. Length of the wire L1 equals to 1 meter. Let the diameter of wire cross section be D1 and resistivity be rho 1. Now, cross-sectional area of the first wire A1 equals to pi by 4 into D1 square. Expression for resistance of the first wire R1 equals to rho 1 into L1 divided by A1. For second wire, given length of the wire L2 equals to 4 meters, that is equal to 4 times L1. Let the diameter of wire cross section be D2 and resistivity be rho 2. Cross-sectional area of the second wire A2 equals to pi by 4 into D2 square. Expression for resistance of the second wire R2 equals to rho 2 into L2 divided by A2. According to the problem statement, diameter of the second wire is double of the first. That is D2 equals to 2 times D1 and its resistivity is double of the first, that is rho 2 equals to 2 times rho 1. Now cross-sectional area A2 equals to pi by 4 into 2 times D1 whole square, that is equal to pi times D1 square. Therefore, A2 equals to 4 times A1. Resistance of the second wire R2 equals to 2 times rho 1 into 4 times L1 divided by 4 times A1, that is equal to 2 times R1. Given R1 equals to 5 ohm, therefore R2 equals to 2 into 5, that is equal to 10 ohm. A silverware has a resistance of 2.5 ohm. We have to determine the resistance of a manganese wire having a diameter half of the silverware and 1/3 length. The resistivity of manganese is 30 times that of silver. Let us first write down the given data. For silverware, resistance Rag equals to 2.5 ohm. Let the length of the wire be Lag, diameter of cross section be Dag, and resistivity be ρag. Therefore, cross-sectional area AAG equals to pi by 4 into DAG square, and expression for resistance of silverware RAG equals to ρAG into LAG divided by AAG. For the manganese wire, let the length of the wire be Lm, diameter of cross section be Dm, and resistivity be ρm. Therefore, expression for cross-sectional area AM equals to pi by 4 into Dm square, and resistance of the manganese wire Rm equals to ρm into Lm divided by Am. According to the problem statement, Lm equals to 1/3 of Lag, Dm equals to half of Dag, and ρm equals to 30 times ρag. Now cross-sectional area AM equals to pi by 16 into DAG square, that is equal to 1/4 AAG. Resistance of manganese wire Rm equals to 30 times ρag into 1/3 Lag divided by 1/4 AAG, that is equal to 40 times RAG. Given RAG equals to 2.5 ohm, therefore Rm equals to 40 into 2.5, that is equal to 100 ohm. Two wires, one of aluminium and one of copper, offer the same resistance. The diameter of cross-section of the aluminium wire is double that of the copper wire. If the resistivities of aluminium and copper are 0.028 microohm meter and 0.0168 microohm meter respectively, we have to determine the ratio of length of the wires. Let us first write down the given data. For aluminium wire, resistivity ρAl equals to 0.028 microohm meter, that is equal to 0.028 into 10 to the power minus 6 ohm meter. Let the length of the wire be LAL and diameter of wire cross section be DAL. Now the expression for resistance of the wire RAL equals to ρAL into LAL by AAL. Expression for cross sectional area AAL equals to pi by 4 into DAL square. For copper wire, given resistivity rho copper equals to 0.0168 microohm meter, that is equal to 0.0168 into 10 to the power minus 6 ohm meter. Let the length of the wire be L copper and diameter of wire cross section be D copper. Now the expression for resistance of the wire R copper equals to rho copper into L copper by A copper, and expression for cross sectional area A copper equals to pi by 4 into D copper square. Let us now determine ratio of resistances. RAL is to R copper equals to rho AL by rho copper into LAL by L copper into A copper by AAL. Since these two wires offer the same resistance, RAL is to R copper equals to 1. Therefore, ratio of length of wires LAL is to L copper equals to rho copper by rho AL into AAL by A copper. According to the problem statement, the diameter of cross section of the aluminium wire is double that of the copper wire. That is DAL equals to 2 times D copper. Therefore, AAL equals to pi times D copper square. That is equal to 4 times A copper. Therefore, LAL is to L copper equals to 0.0168 into 10 to the power minus 6 divided by 0.028 into 10 to the power minus 6 into 4. That gives us 2.4 is to 1. A lead wire and an iron wire are connected in parallel. Their respective specific resistances are in ratio 49:24. The former carries 80% more current than the latter, and the latter is 47% longer than the former. We have to determine the ratio of their cross-sectional areas. For lead wire, let the length of the wire be LPB, area of wire cross section be APB, and specific resistance be rho PB. Now the expression for resistance of the wire RPB equals to rho PB into LPB by APB. For iron wire, let the length of the wire be LFE, area of wire cross section be AFE, and specific resistance be rho FE. Now expression for resistance of the wire RFE equals to rho FE into LFE by AFE. Therefore, expression for ratio of resistances RPB is to RFE equals to rho PB by rho FE into LPB by LFE into AFE by APB. From this expression, we get ratio of cross-sectional areas APB is to AFE equals to rho PB by rho FE into LPB by LFE into RFE by RPB. Given ratio of specific resistances, rho PB is to rho FE equals to 49:24. According to the problem statement, the lead wire carries 80% more current than the iron wire. That is, current flowing through lead wire IPB equals to 1.8 times IAFE, and the iron wire is 47% longer than the lead wire. That is, LFE equals to 1.47 times LPB. Since the wires are connected in parallel, IPB into RPB equals to IFE into RFE. Therefore, RPB by RFE equals to IFE by IPB, that is equal to 1 upon 1.8. Now, the ratio of cross-sectional areas APB is to AFE equals to 49/24 into 1 upon 1.47 into 1.8. That gives us 2.5:1. An aluminium wire 10 meters long and 2 millimeter in diameter is connected in parallel with a copper wire 6 meters long. A total current of 2 ampere is passed through the combination, and it is found that current through the aluminium wire is 1.25 ampere. We have to calculate the diameter of copper wire. Given specific resistance of copper is 1.6 micro ohm centimeter and that of aluminium is 2.6 micro ohm centimeter. Let us first write down the given data. For aluminium wire, specific resistance rho AL equals to 2.6 micro ohm centimeter, that is equal to 2.6 into 10 to the power minus 8 ohm meter. Length of the wire LAL equals to 10 meters. Diameter of wire cross section DAL equals to 2 millimeters. Let us now determine cross sectional area of the wire. AAL equals to pi by 4 into DAL square, that is equal to pi by 4 into 2 square, that gives us pi millimeter square or pi into 10 to the power minus 6 meter square. Now we shall compute resistance of the wire. RAL equals to rho AL into LAL divided by AAL. Using values we get 2.6 into 10 to the power minus 8 into 10 divided by pi into 10 to the power minus 6. That gives us 0.08276 ohm. Given total current I equals to 2 ampere, current flowing through aluminium wire IAL equals to 1.25 ampere. Therefore, current flowing through copper wire I copper equals to I minus IAL. Using values we get 2 minus 1.25, that is equal to 0.75 ampere. Since the wires are connected in parallel, IAL into RAL equals to I copper into R copper. Therefore, resistance of the copper wire R copper equals to IAL by I copper into RAL. Using values we get 1.25 by 0.75 into 0.08276. That gives us 0.1379 ohm. For copper wire, we have computed resistance R copper equals to 0.1379 ohm. Given specific resistance of copper, rho copper equals to 1.6 micro ohm centimeter, that is equal to 1.6 into 10 to the power minus 8 ohm meter. Length of the wire L copper equals to 6 meters. Expression for resistance of the wire R copper equals to rho copper into L copper divided by A copper. Therefore, cross-sectional area A copper equals to rho copper into L copper divided by R copper. Using values we get 1.6 into 10 to the power minus 8 into 6 divided by 0.1379. That gives us 69.6 into 10 to the power minus 8 square meter. Again, cross-sectional area A copper equals to pi by 4 into D copper square. Therefore, diameter of wire cross-section D copper equals to root over 4 times A copper divided by pi. That is equal to root over 4 into 69.6 into 10 to the power minus 8 divided by pi. That gives us 0.94 into 10 to the power minus 3 meter or 0.94 millimeter. So today we have solved a couple of numerical problems on resistance. By solving these problems, we have learned how to compute resistance of a conductor, comparing it with another conductor of known resistance. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.